the, the topic was already said, so let's not waste too much time on it. So our motivation was that the inherent defects that obviously the additively manufactured parts have, like defects on the surface, roughness, and porosity, might have a different impact on mean stresses than the standard materials, and also that this static stress component impact on the fatigue life in additively manufactured steel, the maraging steel 80 and 300 is not well and sufficiently recognized in the literature. So we decided to take this approach, and our study aims to estimate the effect of the suppressed static stresses, the mean values, under various cyclic axial torsional loadings, including the in-phase and out-of-phase loadings of the additively manufactured maraging steel. Our experiments, fatigue tests, were done under various loading paths, 22 to be exact, for axial and torsional in-phase, out-of-phase stresses with stress ratio -1, -0.5, and 0. And then we use a novel application of data-driven approach, Gaussian process for regression, to estimate the effect of static stress component on the fatigue life. So to shortly characterize the material, we use the EOS maraging steel. The company's name for this powder for this steel is MS1. And we use our device, the 3D printer. It's an EOS M2800. It's a laser bed power bed fusion, and it was done in nitrogen atmosphere. The powder morphology is on the bottom of the slide. The specimens we used were hollowed with my own feedwalk specimens. The wall thickness was nominally 0.5 millimeter, and they were all printed in the vertical matter. We did more than 300 specimens of that type, and the laser scan strategy was as shown on the slide, with a 67-degree angle change between the layers and additional contouring on the outer and inner diameter of the specimens. On the next slide, we could maybe in another slide we will see the effect of the contouring. So after the printing, the specimens were cleaned by shot spinning, with glass beds of around 90 to 150 micrometers diameter, and no further machining, nothing else. Then they were aged hardened for 6 hours in 490 degrees. We did a lot of tests to check the best temperature for this, and it turns out that the one that the manufacturer says it's the best was actually the best for the fatigue life. So we stayed with 49 degrees, and using the DIC, we received standard methods too, but at the end, using this DIC, we got the poison ratio and other parameters for the steeling. So very durable material. As you can see, the ultimate strength is over 2 gigapascals. The yield strength is close to 2 gigapascals for tension, and 1,300 and 1,200 over for torsional stresses. The hardness is around 650 meters. What was on the left side of the slide, you can see the path of the laser. Actually, on the specimen, you can see the contouring. It's hard to see, but on the outer layers of the specimen, this is the 0.5 millimeter wall. You can see the 67 degrees on the bottom, and you can see the lines of contouring. But what was the biggest problem? Also, you can see the porosity, but the biggest factor for the fatigue crack initiation was the the places where the specimen was a bit thinner, we had these values. They were like 30, 40, maybe sometimes 50 micrometers deep on both sides. On the outer inner layers, there was not really a big difference where they were, and at the end, the specimen, the fragmentation was almost always in those valleys, and most often from the outer, the inner layer, but maybe that was just a coincidence. So for the next slide, this is the optical profiler from the specimens. On the left, you can see the inner layer of the specimen, on the right, the outer, and the valley on the right side is clearly seen here, the blue hole in it. On the left, you can see the spots of reddish color. This is not actually specimens; those are the residuals of powder that will stick to the specimens. And even though we use the shot filling, of the inside of the specimen was not sufficient. It didn't have a net impact on the fatigue life, but yeah, it was there, and it can be seen here. But the surface parameters are fairly similar for both layers, outer and inner layers of the topography of the material. We also did tomography scans for the specimens firstly to accurately measure the specimens, the thickness and stuff like that, to look for the pores. The porosity of the material was between 0.7 to 1.15%, so not so bad. And you can see the valleys here on the B is on the inner surface, on the left you can see on the outer surface. So this was just, in this case it does not really that matters a lot, but yeah, it's important. So the test, let's get to the test. 22 logging paths from standard axial test compression through torsional tests and combinations in phase, out of phase. We used two machines. First one was the Electropulse E10,000. It's up to 10 kilonewtons machine with 100 newton-meters of torque, and a bigger brother of this machine for 100 kilonewtons and 1,000 newton-meters. We needed that for the lower, the higher stresses, lower life. Frequency was dependent on the loadings and varied from 1 to 30 hertz. We used to control force and torque, and the fatigue regime was roughly from 300 to 200,000 life cycles. And the stress ratio, like I said before, was from -1 through -0.5 and 0, and the phase shifts were 0 and 90 degrees. The ratio of torsional and shear stresses to normal stresses was 0 within case of yeah, it was supposed to be 0.5 and 1, but doing the additional measurements of the specimens, they were a bit different diameters than we thought they were, so it went to 0.49, which was actually not a big deal because some models didn't want to work with this. I mean, 0.5, the calculations were great. 0.49, everything went to other places. So the Gaussian process models, we got all the data, and we used 4 predictors. So for both axial and torsional, we got amplitudes and the mean stresses. So for predictors, outcome was the logarithmic value of fatigue life, and we randomly selected many times. 90% of the points were used to train the model, and the rest 10% we used to fact check it. Only during the training, I mean, actually standard procedure were used, but we had one physics-based constraint. It was that when the stress amplitude lowers, the fatigue life should be higher. This is standard, as it should be on the SN curve, right? And we use error index validation for the training data. Maybe it's also a standard one. And then when we got the model trained, we use it on the test, on both actually sets, but we started to use the last 10%, and we use agnostic interpretation methods. First was the partial dependence plot, PDP, and the second one, individual conditional expectation, ICE plot, which will be shown on the further slide. So first, the main explanation. It means mean absolute percent error. It just calculates all of the ICEs for every specimen. But I will do it better shown here. So we had 4 groups on materials of data sets: uniaxial loadings, torsional loadings, and then multiaxial in-phase loadings and multiaxial out-of-phase loadings. And for each group and each specimen, the ICE parameter was calculated. This is the gray lines. I mean, the dark spots are the actual tested specimen, and within every one of each, we changed the value of the mean stress for this specimen. One of them, in this case, the actual mean stress, sigma m, we change it from 0 to the maximum of the mean stress in this data set, in the test we did, basically. We have to use the model within the boundaries of the data we train it on. So in this case, I mean, it's cut here. I think it was 600 or something like that. So for each one, we have the gray line, and the dark the red one is the partial dependence. It's basically a random mean value that shows the impact of the change of the static part of the stresses on the fatigue line. And further, so first the model. This is on the left. You can see the training data for three paths with the average error of 2.67%. You can clearly see that most of them are within the 2 times boundaries. And on the right side, the remaining 10%. Obviously, it was not always, I mean, it was random, so sometimes the 10% were not from every single path, so we try to review it to get the results on at least 1 to 2 specimens of one, basically. For each path was available to fact check. We did it 12 times for this process only. So I will show you. Could you please? Oh, okay, never mind. So this is the mean value. I mean, it's a mean value of a mean value because we did 12 times this process, and then we averaged all the made values for those 12 times, and you can see them for the training data, the test data for all 4 sets. They're actually almost equal. I mean, there's no significant difference, especially for the testing data when it was 1 or 2 specimens for the set that was not taken into the test. It has a bigger impact on the percentage, but it's still, they are all in the boundary. The model work very good with that. So no, oh, okay. So I think I skipped a slide, or maybe not. No. Crack paths under uniaxial loading. Like I said before, there was porosity, obviously, but in most cases from the valleys, the crack initiates, and for 66% of those initiated crack, there was no pores within close, approximately close distance from the place when it initiated. For 22, there was a pore very close to the valley, but we didn't see, we couldn't find any impact on the actual fatigue life for those specimens. So probably it was just a coincidence, but the pores were not so important. In other tests, we found a way to get rid of most of the pores, but again, no actual impact on the fatigue life. The values are much more important, I would say. From the tomography, we can see for torsional test, because the values were very important for the moments where the actual stresses were much, were the reason the specific crack. For torsional stresses, it was more like the crack was between the layers. It was going around the specimen. Sometimes went from one process to the torsional, the vertical ones, but only with a high number of cycles. With the lower life, the most important part was the maximum shear stress planes in this case. On these photos, the dark places are the pores, but we shouldn't be too much. Shouldn't care too much about them at this point. So the result for the mean stress, like I said, we have uniaxial loadings, torsional and uniaxial torsional, and then in phase and out of phase, and the impact of sigma m, so the actual stress, and the impact of torsional loadings, mean values. So for the uniaxial loading, there is a visible impact of the change of the static stress value. It can be seen on the plot here. It's best to look at the red line. When the closer to the left we are, I mean, you can see that the line declines, and you can see that the fatigue life predicted for the specimen gets lower while we increase the stress. It's also like this in torsional, but it's less important, let's say that. For the in-phase loadings, you can see this. We can see the impact. Obviously, this is the values are quite lower. I would like to point out, because we get up to 280 megapascals compared to 800 on the top. There is an impact, but it's somewhat equal between axial and torsional stresses. It lowers, right? But it lowers roughly the same for both of them. And for the last out-of-phase loadings with the same level of stress values, we can see the impact for the out-of-phase of axial stresses, but the impact of torsional mean value for the out-of-phase test was zero. There was absolutely no impact. It might be that we just weren't, we didn't go far enough, high enough with the stress value. Maybe, probably, we have to test it later, but the line is absolutely flat here. Yeah. It will be seen better on this slide, because this is all the 12 cases we did to calculate the MAVE, 12 different approaches there. I mean, a bit higher or lower, but still you can see the trend for each 12 of them. For the uniaxial is the black one. On the left is the axial component, tension compression. On the right side is the torsional component. And all on the left, one of them goes down faster, the second one slower, but yeah, there is an impact. On the right side, for in-phase, the blue lines, you can clearly see the impact, and it's even higher than in the axial, in the just torsional without tension compression. But the magenta line, probably magenta, it's clearly there's no impact here. So going to the conclusions. Oh, I think I skipped. Okay. Yeah. The mean stress effect is higher for uniaxial loadings than for torsional loadings. It is attributed to the higher sensitivity of the material for axial loadings due to surface peaks of the specific state. Out of phase loading, the actual static stress component has a significant impact on the fatigue life, while the torsional one has absolutely no impact. We need to further analyze this one. And the effect of actual and torsional static components are nearly equal under multi-axial in-phase loadings paths. And in general, the Gaussian process model with the application PDP-NICE can be used to estimate the effect of static and alternating stress component of the